to talk about relative motion, velocity, and how frame of reference is really important. So the other day, I stood right under the little paper that says 0 on the ceiling, and I posed this question. And the question was, am I moving? Now remember, for something to be moving, its position has to change. And some of you said, no, I'm not moving because my position is not changing relative to you guys. Some of you said yes after I kept on asking, because technically the earth is both rotating and revolving, and so I am moving relative to some grander, larger frame of reference. So this section is all about how the velocity of an object can change depending on the observer and that observer's frame of reference. So for example, you're driving down the road in your car and you're going 80 kilometers per hour north, and a car passes you going 90 kilometers per hour north. You, who were in the 80 kilometer per hour car, see the faster car. It looks like relative to you, it's only going 10 kilometers per hour. However, relative to someone standing on the side of the road, the 90 kilometer per hour car is going to be moving 90 kilometers per hour if that person is standing at rest on the side of the road. So the motion of that 90 kilometer per hour car, or the velocity, is different depending on the observer, whether you're in the 80 kilometer per hour car or whether you are sitting or standing at rest on the side of the road. So let me explain how we kind of look at these different velocities, because it's kind of hard to keep them all straight. So here we're going to call the 80 kilometer car, we're going to call that the velocity of car 1 relative to the earth. Okay? So relative to the earth, you're in the car going 80 kilometers per hour north. That's the velocity of car 1 relative to the earth. Okay? The 90 kilometer car, we're going to call that the velocity of car 2 relative to the earth. Okay? And then if you're in that slower vehicle, we could say that's the velocity of car 2 relative to car 1. And that's the whole 10 kilometers per hour north. Okay? And then we would have the person standing on the side of the road, and that would be the velocity of car 2 relative to the earth, because you, standing on the side of the road at rest, you're on the earth. Does that make sense? Okay. So there's this an equation, and it's vector addition. And here's the thing, is velocity is a vector quantity, and you can add velocity vectors, all right, to get this resultant velocity vector. So we have this equation, and I'm going to use this example. So here we have the velocity of car, let's say car 2 relative to the earth. And that's the vector. So we're going to draw the arrow. And then we have the velocity of car 1 relative to the earth. And then we have the velocity of car 2 relative to car 1. Okay? So if we plug this in, we know that the velocity of car 2 relative to the earth is 90 kilometers per hour. And that's north, so we'll put positive here. We know that velocity of car 1 relative to the earth is positive 80 kilometers per hour to the north. And so we know that the velocity of car 2 relative to car 1 has to be positive 10 kilometers per hour. Makes sense, right? And so this equation is really important. And we use these subscripts, to help us keep everything straight. But it's just vector addition, okay? And this equation is really important, and it's going to look different depending on what's moving, what's going on, okay, the problem. So let's look at another one. And this is a classic one. So a passenger at the rear of a train traveling at 15 meters per second relative to the earth throws a baseball with a speed of 15 meters per second in the opposite direction of the motion of the train. What is the velocity of the baseball relative to the earth as it leaves the thrower hand? And then there's this Mythbusters video that I want to show you after we're done with this. So I'm going to draw a picture, because I like pictures. So let's say we have our train here. And the train is moving to the right. We'll just say that. It doesn't tell us that. We're just going to assume. So this would be the velocity of the train relative to the earth. And that's 15 meters per second. And we'll just say to the right here is positive. Okay? And then we have this person back of the train going to throw this baseball in the opposite direction. So the baseball here, this would be the velocity of the baseball relative to the train, because the person throwing the baseball is in the train. All right, and then we have, let's say, this observer at rest, the side of the train tracks. Okay, this would be, and he's on Earth, right? He's on the Earth. So this would be the velocity of the baseball. He would see the velocity of the baseball relative to the Earth. And again, these are all vector quantities. So here's our equation, vector addition, right? The velocity of the baseball relative to the Earth is equal to the velocity of the train relative to the Earth plus the velocity of the ball relative to the train. Okay? So if we plug in here, we can see that the velocity of the train relative to the Earth is positive 15 meters per second. The velocity of the ball relative to the train, now remember, he's throwing it in the opposite direction, and velocity is a vector, so direction is important. That's going to be negative 15 meters per second. So according to this, the velocity of the ball relative to the Earth is 0. So this person standing on the side of the train tracks is just going to see the ball drop straight down. It's not going to move right or left because the velocity right or left relative to the person standing on the side of the road, or velocity of the ball relative to the Earth, is 0. So he's going to see the ball drop straight down because gravity is going to be pulling it down. Now, we can also add velocity vectors graphically. All right, graphically. So adding vectors graphically. So our equation here is this one right here. Okay, so remember adding vectors graphically, graphical method of adding vectors. We have to determine a scale. Now I'm going to do things a little different because I've got this grid paper going on. And these are pretty simple measurements. So what I'm going to do is I'm going to say that 1 meter per second is equal to 1 of these little squares. So I'm going to use the squares in this case to help me with this graphical method. Now I'm going to draw the vectors to scale. So I have the vector of the train relative to the Earth, and that is positive 15 meters per second. So let's see. If I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I'm going to go right there. So that should be the velocity of the train relative to the Earth. That should be 15 units. Okay, that's perfect. We draw arrows to represent vectors. And then the velocity, again, we're doing vector addition. The velocity of the ball relative to the train, we're going to add these vectors tip to tail. That's going to be here, the velocity of the ball relative to the train, and it's negative 15 meters per second, so negative 15 squares. And again, I'm adding tip to tail. Now, technically, those two vectors are supposed to be on top of each other, but it's really hard to see. So then my resultant vector is just 0. And the resultant vector in this case represents the velocity of the ball relative to the Earth. Okay, so I want to show you this Mythbusters video. And hopefully this will work. There we go.
So what are you so excited about?
Well, it's our turn to try a new type of myth, the physics thought experiment.
Great. Something to get the old gray matter working.
So here's how this one goes. Let's say you're driving along in a car at X miles an hour. You throw something out the back in the opposite direction at the same speed. Does it just fall straight down?
Build an air cannon, fire a soccer ball at 60 miles an hour. We'll do it again inside of a moving vehicle going 60 miles an hour. See if the energies cancel each other out, and we get a vertical drop.
Love it. Let's do it.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air. It stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector addition! Yay! We canceled out velocity.
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.